Okay, in this video, we're going to be looking at the graphs of our three basic sine, cosine, and tangent trig functions. First off, let's look at the graphs of our sine and cosine functions. And again, you could find these by taking your common sine of 0, sine of 30, sine of 45, sine of 60, sine of 90, plotting those points as well as the cosine. Notice that with our sine graph and our cosine graph, notice that the cosine function is a horizontal translation of the sine function. They're the same graphs, just shifted over. Now, it is important that you know which is which. And we know that the sine of 0 is 0, and the sine of 0, the cosine of 0 is 1. So that's a tip that you can use to see which is which. Any transformation of a sine function is called a sinusoid. Therefore, sine and cosine functions are actually called sinusoidal functions. So, functions that repeat at regular intervals, as these, another name for them are periodic functions. Because again, what happens is this thing comes up, down, back up, and then it does the exact same thing again, as you can see over here. Same thing with the cosine function. Now, let's define a couple of words here. First one being period. The period of a function is the length of a cycle. And now this period again can start at any point on the graph. Let's scroll back up and look at our sine and cosine functions and talk about what a period looks like. Notice that one complete cycle, if you start here, and then again it can start at any point. Start here at the top, it goes down, comes back up to the top. Then it would actually go through the exact same thing again. The distance from one point there to another point of that cycle, one complete cycle, is called the period. And notice over here what I did. I started at the middle of the function. We go up, we come back down, and then we start over again here. So the distance from here to here, one complete cycle again, is called the period of the function. Next up, the amplitude. The amplitude is half the distance between the minimum and maximum values. It's kind of like the height of a function, of a curve here, or a wave. The distance from, I guess you could say it's the distance from like this equilibrium, the center point. It's the distance from there to the top. That would be the amplitude. I'm just going to put amp. Or the distance from the center down to the bottom. That's another amplitude there. Or you can find, again, the height, the total distance from the top down to the very bottom. The range would be half the distance between the range of this function. So you could take from the top down to the center of this graph, that would be an amplitude, or again from there to the bottom, that would be another amplitude. So half of the total distance. So given this function, a normal sine curve, as you can see here, a normal sine curve is going to have an amplitude of 1, and it's actually going to have a period of 360 degrees. However, we will talk about these transformations here, and the amplitude of these curves, if there's a number out front, and again, we'll get more into the transformations later, but the amplitude is going to be the absolute value of whatever that A value is down front. Normally it's 1, but again, it could be changed. The period of a function, like I said, is normally 360 or 2 pi. However, if there's a number being multiplied by the x here, then our period is now actually going to be 2 pi over the absolute value of b. So let's identify some amplitudes and periods of these functions. Again, the amplitude can be found simply out front. So the amplitude of this function, since the number 1 is out front and out in front of the sine function here, the amplitude will be 1, and the period is going to be, okay, normally 2 pi. However, if there's a number in front of that x value, it's going to be 2 pi divided by that number. So in this case, our period is going to be pi over 2. And again, that is a transformation. A normal sine curve has a period of 360. However, if you remember, if there's a number being multiplied by x, that's going to compress. It's going to compress by a factor of 1 over, by the reciprocal. So if you take 1/4 of that 360, you're going to get 90, which again is what our new period is, 90 degrees. Number 2, let me zoom in. The amplitude of this function is going to be the number out front, the absolute value. So this has an amplitude of 7/2 or 3.5. The period, again, if there's a number in front of this x, it's going to stretch and compress. It's going to be 2 pi over that number. So therefore, since there's no number, this has a period of 2 pi. Number 3, the amplitude is the absolute value of this number out front. So here the amplitude is going to be 5. The period is going to be 2 pi over, if there's a number in front of the x, 2 pi over that. Flip and multiply, so the period of this function is going to be 6 pi. Next one, the amplitude is going to be the absolute value of this number. So in this case, the amplitude is going to be 2. The period is going to be 2 pi over any transformation in front of the x, which would be 4/3. Flip and multiply, you get 6 pi over 4 or 3 pi over 2 when you reduce it. So there's your amplitude and period. Number 5 says identify the amplitude and period, then graph the function. So here the amplitude is going to be 2. The period is going to be 2 pi for the reasons we just said. Now let's look at some points on this graph. Again, what I would do is I'd plug in some values, plug in maybe 0. We know the sine of 0. When we plug that in, the sine of 0 is going to be 0 multiplied by 2, and you still have 0. And let's take maybe where our highest points and lowest points are. I know the sine of 90. If we go over to 90 degrees, which is right here, which is pi over 2, the sine of 90 is going to be 1. However, when you multiply that by 2, you're going to get 1 times 2, which is 2. The sine of pi, which is the sine of 180, is 0. 2 times 0 is 0. The sine of 270, which is right here, is going to be -1. When you multiply that by 2, it gives you -2. So you can see kind of what your graph is going to look like here. Let's put a few more points on this graph and let's connect our dots. And there is your graph. And again, you can see that the period, if you were to start here, it would start over here. So from 0 over to 2 pi, that'd be a period of 2 pi. And the height or the amplitude right here, the distance from the center point up to the top, that has a distance of 2. The next one, the period, the amplitude first should be 5. The period should be 2 pi divided by any number in front of the x, which is 1/2 here. That's going to give you a period of 4 pi. Again, simply pick out some numbers such as 0. Plug it in. Plug in 0, you get 1/2 times 0 is 0. The cosine of 0 is 1. 5 times 1 is 5. So when you plug in 0, it gives you 5. Plug in a few more, see what you get. And there's your graph of this function. I plugged in 0, got 5. Plugged in pi and got pi over 2 here. That'd be the cosine of 90, which is 0 times 5, which is 0. So just pick some points there, plug them in, and you can see again the amplitude is the distance from here to here, which is 5. The period looks like this thing starts over. Well, it's going to take like from here all the way over to here. That's from -2 pi up to +2 pi to start over again, and that is a distance of 4 pi. Number 7. -3/2 cosine of 4x. Again, our amplitude should be a +3/2. The period should be 2 pi divided by the transformation in front of the x, which is 4. So it's going to be pi over 2, which is 90 degrees, should be our period. Plug in some points and let's graph it. So this one was a little bit trickier to graph. Now, something you do need to notice that if this is pi, there are 1, 2, 3, 4 division lines. So this is pi over 4, 2 pi over 4s, which would be pi over 2, 3 pi over 4s, and then 4 pi over 4s, which is pi. So each one of these tick marks on your graph is counting pi over 4. So as I plugged in each one, it was just oscillating pretty much between a +3/2 down to a -3/2. So you can see here that from one height here to the next height, that the distance from here to here is 2 of these tick marks, which is 2 pi over 4s or pi over 2. So that is the period of this function. The amplitude, again, from either lowest to highest, you can count it that way, or I like to come right here to the middle and then count up to the highest, which is a distance of 3/2. Okay, number 8. The amplitude, again, can be found with the number out front, the absolute value of this number, which is 1. So that's going to be the height of our function here, and the period is going to be 2 pi, and then let's transform that by dividing by 8/3, or multiplying by the reciprocal. You could actually do so times 3/8. Cross cancel, that's a 1 and a 4, so that's going to be 3 pi over 4. Now, from here on out, I'm going to actually use Desmos to help us with the graphs of the rest of these. So I'm going to graph this thing on Desmos and translate that graph over to our paper here. And here you see our graph in Desmos, and I've set up actually the parameters identical to what we have it on our paper. Notice here that my graph crosses at 0, 0, and then again 3 pi over 8, and at 3 pi over 4. So we can take those 3 points and let's go ahead and plot them on our graph. So 0, 0. Again, 3 pi over 4, that one's easy to find, and then directly in between the two would be 3 pi over 8. And then you have your maximums and minimum points, and we can use our amplitude. This thing will never go above 1 and never come below -1, so you could actually look at your graph here. From 0, 0, it goes down, and it's going to go down to directly in between those 2 points to a minimum. In between these 2 points, it'll go up to a maximum. So as long as we get a pretty accurate, pretty close sketch of what it looks like, and then we're just going to repeat that exact same thing over and over. We're going to come down. So every 1.5 tick marks, this thing is crossing the x-axis. So it's going to cross in these spots. And then we're just going to come down to minimums and go up to maximums in between those points. Keep doing that over and over. Connect your dots, and here's what your graph's going to look like. And there is your graph, and you can see that we do have an amplitude of 1, and that period from here to here is a total of 3 pi over 4. Number 9. Again, y equals -5 halves times cosine of 2/3 x should have an amplitude of 5 halves, which is, again, if you were to divide that, 2.5. And the period should be 2 pi divided by 2/3, which would be 2 pi times 3 halves. Flip and multiply. The 2's cancel, and that's going to give you a period of 3 pi. Again, I'm going to flip over and use Desmos and to help us graph this. And here is a picture of my graph. And I do notice I cross here at 3/4, or 3 pi over 4, cross at -3 pi over 4, and here at 9 pi over 4. So let's go ahead and put those intersection points on our x-axis. So again, it was at 3 pi over 4, 9 pi over 4, -3 pi over 4, and -9 pi over 4. And then our maximums and minimums will occur because of its symmetry directly in between it. Notice that we do have an amplitude again of 2.5. So right here in the middle, we're going to come down 2.5. I'm going to go to the middle of these 2 points here, and I'm going to go up 2.5 and do the exact same thing over here and connect my dots, and there is my graph. And you can see once again that the distance from here to here, if you were to measure it, should be a distance of 3 pi. That's one complete period. And we already know that our amplitude here from the middle up to the top is 2.5. Next up, should have an amplitude of 4, the number out front, and should have a period of 2 pi. We're going to have to divide that by 2 or flip and multiply by 1/2, and we should have a period here of pi. Let's use Desmos to graph this thing. And here is a picture of that graph. And notice our x-intercepts are here at 0, pi over 2, pi, and so on and so forth. So let's go ahead and plot those points on our graph. So again, 0, pi over 2, pi, and those x-intercepts on our graph is occurring every 2 tick marks. So there's all my x-intercepts. And then I just, if I can get my maximums, and they occur directly in between my maximums and minimums, will occur directly in between my x-intercepts. And notice that how high my graph goes. It goes up to a value of 4. So therefore, let's come and directly in between these, I'm going to go up to 4, put a maximum. Between these 2 points, come down to -4 and put a minimum. And continue that on. And then we're just going to simply, again, connect our dots, and we will have our finished graph. And there is our finished graph, and you can see we do have, again, an amplitude of 4, and you can check the period here. From here to here is a distance of pi units. Next up, let's take a look at the graph of a tangent function. And you can see the parent function over here and kind of see what it's going to look like. The tangent function is undefined, however. You will have vertical asymptote lines. It's undefined for certain values of x. Therefore, the tangent function has vertical asymptotes. The tangent function does not have an amplitude. It's not a wave like the sine and cosine is, so therefore no amplitude. The tangent function, a normal tangent function has a period of pi instead of 2 pi, so therefore the period of of any transformation of a tangent function would be, again, the pi over the absolute value of b. And the asymptote lines are odd multiples of pi over 2 times the absolute value of b, which you don't have to memorize that, but that's where they are going to occur. On this one, we're going to identify the period. Then we're going to graph each function. We're going to show the asymptote lines on our graph. So the period of this function, a normal period is going to be pi. However, if you have a number in front of this x, it's going to transform it by stretching or compressing it. But this one is going to have a normal period of pi. There will be a vertical stretch here. So let's, again, use Desmos and graph this thing. And here's a look at the graph. And notice that we have x-intercepts at 0. Have another one over here at pi. We have another one at 2 pi. And again, those asymptote lines will occur directly in between those values. So let's go ahead and plot our x-intercepts here. Again, it occurred at 0, pi, 2 pi, negative 2 pi. And again, those asymptote lines are occurring at pi over 2, 3 pi over 2, and so on and so forth. So you can, if you would like to, you can draw those asymptote lines. And I'm going to go ahead and put those on my graph. And once I have these values, I can now just simply follow these asymptote lines. And it looks a lot like an x to the third type graph in between here. So coming up and then go down and approach this asymptote line on the other side and continue doing that on and on, and you're going to see your tangent function. So there is a picture of your graph. And again, notice that because of the period being pi, that these asymptote lines are spaced out pi units apart. Here you see pi over 2 and 3 pi over 2, which is again a unit of pi apart. Next up, let's graph this. Negative tangent of 1/2 x. Again, normally our period is pi. Let's divide that by the number in front of the x. Flip and multiply, you're going to get 2 pi units. Plug in a value like 0, and you can use that to help you graph. The tangent of 0 is 0, negative 0 is still 0. You can find those asymptote lines by using the formula that we gave you, the pi over 2 times the absolute value of b, and you could actually plot those. And that would give you, when you plug in the 1/2, that's going to give you pi. And again, it's the odd multiples of pi. So the 1 pi, the 3 pi, the negative 1 pi, the negative 3 pi, that's where those asymptote lines are going to occur here. And here is a look at that graph, and you can see those asymptote lines at negative 1 pi, positive 1 pi. You would have another one again at 3 pi. Your x-intercepts occur at 2 pi, 0, and negative 2 pi, so you could go ahead and plot those on there. So negative 2 pi, positive 2 pi. You did have that asymptote line here at negative pi and another one here at positive pi. Also, because of this negative being out front, it is going to flip your graph over, so it's not going to look exactly like your previous graph looked. It's going to look more like this. It's going to be a vertical flip there, so let's do a couple of these. It's going to look there, and then this value over here approaches this way and comes up through here, and there's a look at what your graph would look like. Number 13. Y is equal to 5/2 tan of 2x. So your period is going to be pi divided by your b value, which is going to be 90 degrees. You can use Desmos to find some values and graph it, or again, you can use your formula for your asymptote lines to find those. So again, we said the asymptote lines are going to occur at pi over 2 times the absolute value of b, the odd multiples of that. So plugging that b value in, which is here, That's going to give you a value of pi over 4. So that's going to be 1 pi over 4, 3 pi over 4, 5 pi over 4, negative 1 pi over 4. That's where those asymptote lines are going to occur. And there I went ahead and plotted those asymptote lines here. Using Desmos, you can see a look of that graph. You can kind of see what's going to happen there. And we can simply put our x-intercepts in between here and just follow those asymptote lines with our tangent graph, and there's what it's going to look like. And you could continue this on and on and on, because again, this is a periodic function. It repeats over and over and over. And again, the period of this function, if we did it correctly, should be pi over 2. The distance from here to here is going to repeat every pi over 2 units. And then number 14, the period here should be, again, pi divided by whatever your b value is here, which is 2/3. Flip and multiply, you're going to get 3 pi over 2. You can find your asymptote lines if you would like. We're just, again, going to use Desmos to graph this. And here is what it looks like on Desmos. Again, you have x-intercepts here at 0. You got another one over here at 3 pi over 2 and negative 3 pi over 2. Your asymptote lines will occur here in the middle at 3 pi over 4, negative 3 pi over 4, negative 9 pi over 4, and so on and so forth. We're just going to transfer that over to our paper, and here's our graph. And you can see there the asymptote lines. And again, you can use these. You can use table of values to graph these. You can use your calculator, plugging in values, make a table, use Desmos, use all those resources that you have available.